Welcome to our in-depth analysis on the invention and evolution of the turbo. This narrative embarks on a fascinating journey spanning centuries, taking us from initial concept to modern application. You may have seen the turbo's role in bulking up performance in vehicles, aircraft, and even power plants. Nevertheless, do you know how this integral piece of hardware was fabricated or the rigors faced in perfecting it? Anticipate uncovering daunting challenges, groundbreaking achievements, and the ambitious characters behind the turbo's intricate history. Acknowledging the turbo's origin demands discussions on steam technology. A few centuries ago, the birth of the turbo can be traced back to the genius mind of Leonardo da Vinci. Among other inventions, the ambitious Italian visionary conceived the fire-driven turbine, an early prototype of the modern-day turbo. Da Vinci foresaw a device propelled by steam that could power machinery. His Herculean cognition left a seminal mark on the eventual revolution of the turbo. It wasn't before André-Marie Ampère, French physicist and mathematician, transformed Da Vinci's theoretical turbine into a physical embodiment. He succeeded in demonstrating the practical application of steam to spin a rotor and turbine wheel in 1827. Ampère's pioneering endeavors eventually molded the foundation for the technological advancements seen in today's turbines. This progress wouldn't have been possible without the stalwart contributions of Ampère and his contemporaries. With steam turbines taking shape, further credit must be accorded to the Swiss engineer, Alfred Büchi. Büchi is the revered inventor of the turbocharger. Contrary to its commonly known usage in vehicles today, Büchi initially designed the turbocharger to enhance power in industrial processes. Nevertheless, his invention still stood as our modern perception of the turbo being pushed towards mechanical and power advancements. Elaborating on his invention, Büchi introduced us to a novel approach. Tramping in the footprints of steam turbines, Büchi optimized the signet of waste from the engine into a power amalgamation. This innovation was achieved by incorporating a twin turbo system, where the first turbine harvested the waste, transferring the power to the second charged turbine. The byproduct was a significant boost in engine performance, which recognized Büchi's hard work and inventive finesse. Büchi's principle showcased a prominent non-nature volume of power amongst traditional automobiles. Thermal compression surged as the heart of the turbo design, implying that an engine's inlet volume could be increased substantially without requiring a larger engine. This concept stimulated a paradigmatic shift in the automotive, aviation, and power generation sectors, consecrating the turbo as a symbol of advancing technology. Evolution of the turbo didn't cease with Büchi's pioneering designs. John Crostwood and Herb Johnson, engineers at Chrysler's Missile Division, played influential roles in refining the turbo's blueprint to facilitate the burgeoning demands of the automotive industry. By focusing on decreasing the turbo's lag, they optimized the size of the turbo's compressor and turbine. These strategic alterations allowed for quicker and more potent bursts, reducing the spatial footprint in an engine compartment. Bridging the reality from concept, the late 1970s was an era of thorny technological fortitude for turbo engines. And to propel these envisioned mechanisms into the real world, fearless car manufacturers like Porsche and Saab started deploying turbochargers in mass-produced automobiles. This spelled the start of seismic shifts in the performance of everyday vehicles. Simultaneously, the adaptation of the turbo extended into rallies, where companies like Audi and Lancia leveraged the high torque and steady output of their turbocharged engines. Equipped with its newly acquired turbo engines, the sport of rallying entered a phase of unprecedented competition, drivers maneuvering with unprecedented power and speed. Not content with merely improving engine performance, engineers focused intently on minimizing lag and increasing reliability. Innovations, such as the wastegate and dual-scroll turbo, became pivotal in countering lag, and were focused efforts to boost sustainability. For instance, the wastegate, designed to control the speed of the turbo and in turn assure safe and efficient functioning. On the flip side, aviation and power generation sectors also rode the wave of turbo leapfrogs. Given the formidable thrust-to-weight ratio, turbo engines were quickly embraced by the aviation industry for their excellent climb and dash performance. This was mainly modeled on low bypass turbofans that formed the crux of most military jet engines. Likewise, the power sector, mainly the natural gas, petroleum, and marine industries, also embraced the turbo. Different types of gas turbines were developed, i.e., industrial and aero-derivative, to function in distinct operating environments. For instance, industrial turbines predominantly powered remote locations and power plants, while aero-derivative turbines were employed in the maritime sector for ship propulsion. Shaping this disruptive innovation was no easy feat. It was intertwined with various technical and environmental challenges. In the automotive segment, high temperatures, pressures and kinetic forces had to be fully understood and managed to fabricate durable and efficient turbo components. This was arduous since the turbo sat in an unforgiving and temperature-volatile engine environment. In the same vein, engineering solutions for aviation turbo engines were challenging. The harsh conditions of travel in the Earth's stratosphere and outer space demanded engines capable of operating at high altitudes and high speeds. These designs needed to endure temperature extremes, gravitating between well below freezing to over the boiling point of water within seconds. The power generation industry faced the unique obstacles presented by natural gas and the maritime environment. Key amongst them was designing turbines capable of withstanding and rejecting the high concentrations of waste heat characteristic of natural gas operations. With marine vessels, engineers had to develop turbines excelling in thermal balance and mechanical strength, fluctuating between full load and off-load conditions. Moving forward, the buzz of electric turbochargers promises to set the upcoming discourse for performance and efficiency. This revolution seeks to realize the performance gap and latency in turbocharged designs by reinforcing electrical power. This combination, it's theorized, could provide the best of both worlds: the torque and efficiency of a turbocharged system and the immediacy of electric power. On that note, another tangent that is also starting to spur is the application of the turbo in new domains: hybrid cars, motorcycles and trucks not conventional till the present. Bridging the sustainable energy world with the high torque, power-intensive function of the turbo is seen by many as the bandwagon for future transportation. The cinema darkens, and the spotlight dims, closing a chapter that started with Da Vinci musing on a fire-driven turbine. We've journeyed through the challenges of harnessing this dream, rode on the back of braking technology, and watched as the turbo evolved into an indispensable element of advanced engineering. The pace at which the turbo marches on signifies a bright future for the world of power, performance, and innovation. Similarly, taskmasters of the power generation sphere also toil in crafting cutting-edge turbines. The advent of ceramic materials, sophisticated blade geometries, and aerodynamic refinements are intended to boost turbine efficiency and power output while downsizing on harmful environmental imposing factors. Despite the dynamic evolution and the past promising innovation, the road ahead, as always, is not without its challenges and uncertainties. The future of the turbo stands at a critical junction, balancing between the tremendous power demands of modern society and the impeding pressures on environmental sustainability. As we tread the pathways of time, the turbo continues to propel us towards power, performance, and sustainable technological advancements. It embodies a chronicle of human creativity running wild with possibilities, consistently pushing towards engineering excellence. The turbo symbolizes mankind's relentless pursuit of advancement, promising an exciting future at the crossroads of physics, design, and daring innovation.